Assalamu alaikum. Welcome to the first lecture of chapter 2. Chapter 2 is linear elastic fracture mechanics, in short LEFM. It's a major achievement for all of us. Chapter 1, introduction, was rather a long chapter divided into two portions, 1A and 1B, just to make it easier for us. And I deliberately took a long time covering it because there were many basic things from your earlier courses on material science, manufacturing, machine design, solid mechanics, etc., which are related to fracture mechanics. We wanted to look at all of them in a new light and in a unified approach as a fracture mechanics base rather than individual different courses. And of course, there were a few things which were new also. So we have done that, alhamdulillah, and you know some very basic ideas of fracture mechanics now. And you also hopefully understand many fundamental basic things of mechanics and stress and so on with a new light. So now, linear elastic fracture mechanics. I always ask you to think on the names. So linear elastic, right? One thing it means, because we are now at a higher approach. Linear, of course, means a straight line, but that is not the main thing. Mathematically, linear means any equation where the highest power is 1. Otherwise, the equation is quadratic or cubic or power law or exponential or other forms. All those other forms are non-linear. Their graph is a curve. But a straight line is the only thing which has a linear curve, and it is a single power. So any mathematics, any mathematical model which can be linear is of course very simple to solve. It is a simple equation rather than an advanced equation of a quadratic nature and so on. And here it is not just linear but elastic. Elastic, you totally know that the material, once the load is removed, returns back to original shape and size, and there is no resultant deformation. So it means that in this chapter we will try to do fracture mechanics which is of linear elastic type, right? So that is how we will see. Maybe it is not realistic, maybe every real problem in the world is a non-linear one, but if a linear elastic model can give us good results with only a little error, then the mathematical simplicity far outweighs the accuracy. That if it is almost accurate, very small amount of inaccuracy, then why should we not go for a linear elastic model? So today we will introduce LEFM. In that we will include the atomic view of fracture and the stress concentration effect of flaws. Then we will start the main LEFM with Griffith energy balance, and maybe we get time to compare critical stress criterion against the energy approach. So that we will see if we get the time. Otherwise, we can stop at the end of Griffith energy balance. I am just showing you this. I do every time, hopefully, that apart from the books that we have as textbooks and so on, we go to the internet or we go into the advanced literature and see how different people are working. So if you see here, this is a CT specimen, the compact specimen, right? The V notch and the standard thickness and so on. So this is used to find the plane strain fracture toughness of the material. But then there are other techniques. If you see incident beam, we are sending a beam of light, and this will be split through these slits into, right, one and another, and they will be red and so on. And so these are advanced techniques. These could be advanced techniques of finding the effect of fracture and the distribution of stresses and so on. So we could do this experimentally, and then we could do numerical model like finite elements or other things. So this is one model, right? This is the actual thing, and they have been divided into different elements and so on. And the elements are, say here, triangular, but they could be others. And this finite element model, if it is successful, is successfully telling you the stresses and so on. The red ones are high, 800 megapascal. The next one's orange is 700 megapascal and so on. So the distribution is there. And then you can show the same stress distribution in a radial type of graph, right? In a radial type of graph, in a contour plot. So these are different things which we are not going to do ourselves, but just to give you a flavor that if any one of you goes further into this study, takes a master's or PhD level course in fracture mechanics, or makes this area later on in the practical life an area of expertise, work somewhere, so then you will be focused, you will be doing only fracture mechanics. You will be either taught or you will learn the different packages and so on that you, right? So this is just to excite you that there is a lot of work that can be done if we understand the basics. So introduction to linear elastic fracture mechanics. Concepts of fracture mechanics before 1960. Before 1960, right? It had started. They were applicable only to materials that obey Hooke's law. You remember Hooke's law is force is directly proportional to deformation. So F is equal to Kx, where K is the spring constant or the elasticity and so on. So materials which obey this, of course materials that obey Hooke's law are all the metals and so on in the elastic range. After 1960, fracture mechanics theories have been developed to account for various types of non-linear material behavior, plasticity, viscoplasticity, as well as dynamic effects, things that change with time and so on, right? So this is new. All of these more recent results are basically extensions of linear elastic fracture mechanics, which was here. Linear elastic fracture mechanics, and then we modify it, we extend it, and we include some plasticity in it, we include some viscoplasticity in it, we include some dynamic effects in it. So in this chapter, energy and stress intensity approaches, two different approaches. The same thing is happening. You are applying stresses, and these stresses, because there are flaws or defects in the material, are having stress concentrations. But the way you look at it mathematically or mechanistically is you find the changes that are happening in the energy or stored energy or work done on the material, or changes in the stress intensity. So we will see these two approaches to linear fracture mechanics. We will see the early works of two major scientists in this area, Inglis and Griffith, and we will introduce to ourselves energy release rate and stress intensity parameters. So this is overall what we will cover in linear elastic fracture mechanics. Of course, the field is large and we are doing just a first basic introductory course. Otherwise, even in linear elastic fracture mechanics, we can go much higher. Later chapters, right? This is chapter 2 in the Anderson book. So there are other chapters which are also based on linear elastic. Chapter 7 and chapter 8 are laboratory testing of linear elastic materials. So linear elastic fracture mechanics, the basic theory is in chapter 2, but chapter 7 and 8, how do we test linear elastic materials? Chapter 9, application of linear elastic fracture mechanics to structures, actual structures, plates and spheres and shells and pipes and so on. Chapter 10 and 11, apply LEFM to fatigue crack propagation and environmental cracking that happens because of corrosion or chemical attack or other things. Chapter 12, numerical methods like finite element analysis, finite difference method and so on, for computing stress intensity factor and energy release rate. So we will not cover all of these. Some we will, some we will not. We will selectively do only those parts which to me, which form a basis which we can understand at an introductory level, and the higher or more complex things we leave for a later course, right? But all these 7, 8, 9, 10, 11, 12 are also chapters which are extensions of the current chapter on LEFM. So let us start fracture mechanics at the most basic level, right? What is the atomic view of fracture? Atomic theory, you know, has been there for a long time. There is the nucleus where there are protons and neutrons combined together. There are electrons in orbits. Orbits are divided into shells and so on. So how can we explain fracture of a material based on the atomic theory? So the most fundamental thing is a material fractures when sufficient stress or work are applied at the atomic level to break the bonds that hold atoms together, right? What is fracture, right? The material is being deformed until it fractures. So what is a solid? It is atoms, and between atoms there are forces that join them together. We work on it, we apply forces from outside until these atomic bonds are, interatomic bonds are broken, and then fracture will happen. The bond strength is supplied by attractive forces between atoms. We will see on the figure on the next page, we have schematic plots of potential energy and force against the separation distance between atoms. We will see that shortly. Equilibrium spacing, when are atoms at a distance from each other, which creates equilibrium, stable, where potential energy is at a minimum. This you will remember in thermodynamics, in all other physics, that the most stable system is the minimum energy system. If you increase the energy, then the particles start to vibrate more, or there is more kinetic energy, and the system starts to become unstable. So equilibrium spacing occurs where the potential energy is at a minimum. Now, if we are wanting to create a fracture, a tensile force is required to increase the separation distance from the equilibrium value, right? And this tensile force must exceed the cohesive force to sever or break the bond completely. Cohesive, normal English, cohesion means to join together, right? So the interatomic bonds are the cohesive force, right? There are forces which join the atoms together, and the work or the energy that you apply or supply should be more than this cohesive force. So this is the diagram. This is the diagram. On the vertical axis is the potential energy, and if this is the zero line, then repulsion on one side and attraction on the other side, and these are, say, the two atoms, the nuclei and the atoms and so on, and x naught is the interatomic distance, and right, as we increase the interatomic distance, this potential energy decreases, goes to a negative maximum, which means attraction, and then comes up, and so the bond energy is there. And here is the applied force, tensile or compressive, and here is the distance still. So the bond energy goes up, goes down, and so on. So this is the cohesive force. And when you draw a tangent and so on, and lambda, of course, is the wavelength and so forth. So potential energy and force as a function of atomic separation. At equilibrium separation x naught, potential energy is minimized and attractive and repelling forces are balanced.